We're happy to host our first webinar for Luxoft in Turkey as part of our series of free online events with famous IT speakers. Welcome, everyone. As we are a young and small team and still expanding our career of experts, this is a very special event for us. Started Luxoft operations in Turkey in May 2022. We are currently presented in 2 offices in Istanbul with more than 80 employees across the country. Our agenda today, it is already announced, so I will repeat it for yourself, is that we have a very special guest speaker today. This is a young and talented woman and an experienced C++ developer. She joined Luxoft as a senior software engineer in 2022. Bengisu holds a degree in computer science and has over 6 years of full-time experience in various fields, including automotive and distributed simulation environments. She loves developing innovative software, learning new technologies, and has a passion for problem solving. Today we will have a 40 or 50-minute presentation, after which Bengisu will answer your questions. Feel free to use the Q&A session function at the bottom of your screen to send your questions to our speaker. As mentioned before, yes, there will be a game with a prize at the end of the session. Be sure that you listen carefully because the game is related to what our speaker is sharing with you today. One of you will have a chance to win a Bluetooth speaker. If you carefully follow the presentation, most of the questions will be pretty easy. Keep your smartphones handy. At the end of the session, you will need them to join the fun. And with that, I would like to pass it over to Bengisu. Good afternoon, Bengisu.
Thanks, Ilyana. Good afternoon. I'm so happy so many joined. Let me share my screen first. And are you guys able to see my screen? I guess so. Then I think I can start.
Yes, all good. Please.
Great. Hello, everyone. Today I'll be talking about WebAssembly beyond browsers and its role as a universal runtime. WebAssembly, or WASM in short, is a new portable compilation target designed to complement JavaScript in browsers. It has its own instruction set for its own stack-based virtual machine, and WASM programs written for this VM can be represented in a compact binary format. If you're familiar with Java, this is similar to Java bytecode and JVM. So WebAssembly has a stack-based execution model and a small instruction set. Because of this, implementing a virtual machine is quite easy. Because WebAssembly is a low-level compiled binary format, instead of a script, it can be quickly parsed, loaded, and executed at near native speeds. WASM programs are called modules, run in a sandboxed execution environment. They have an isolated memory and cannot use external resources unless it's explicitly allowed. WASM instructions are designed so that they can be statically verified before execution. For instance, WASM does not have jump instructions. Instead, it has higher-level control flow primitives, like we call if and while, which makes it easier to verify control flow integrity. WebAssembly does not make any assumptions about the platform. It does not even assume that it will be run on a browser, so it's easy to implement a WASM engine outside web embeddings as well. You can use WASM to write software extensions like plugins. Because the instruction set is small, many programming languages can target WASM as a compilation target. And as a result, you can write and compile WASM modules in your favorite language and practically run anywhere. Here are some quick examples. You can port Doom to your browser by compiling it as a WASM module using mscripten. Disney Plus develops its application development kit in C and compiles it to WASM to easily target many living room devices. You can host any edge application on your Raspberry Pi using WASM Cloud, and the possibilities are endless here. This write once, deploy anywhere premise of WebAssembly may sound familiar to you guys. Just like Java, WASM is also a portable, low-level binary format with a stack-based VM, so people naturally ask if they're in difference. However, Java ecosystem is huge. Unlike WebAssembly, JVM comes with a Java runtime engine that has many base libraries. Java programs and their dependencies are not isolated like WASM is, so they're very hard to sandbox. In contrast, WebAssembly was designed with security in mind. If Java ecosystem could have the same properties, we would still be using applets. Another comparison is between WASM and Lua. WebAssembly is very useful for plugin development because you can embed a WASM host in your application and safely run untrusted dynamic code in there. Lua is also very powerful for plugin development. For example, video game mods are almost explicitly developed in Lua. But in this case, WebAssembly has an advantage over Lua because many languages can be compiled into WASM. And in contrast, if you choose to embed the Lua interpreter for plugins, you are restricted to using Lua and Lua-compatible ecosystems only. And as a use case, Microsoft Flight Simulator supports WebAssembly modules as plugins. So let's get into WebAssembly. WebAssembly's instruction set has only 4 types of numbers. These are 2 integers with 32 and 64 bits and 2 floating point numbers, similarly sized. Signed and unsigned integers are not differentiated on the instruction level. There are no pointer types. Instead of pointers, we use offsets into the memory. These are represented as integers. The memory model is linear. Its size is a multiple of 65K. The WASM module can request more pages if needed, which will be appended to the linear memory. WASM virtual machine is stack-based, much like Java bytecode, as I said earlier. So in addition to linear memory, which is treated like the heap, there's also an implicit operand stack. A WebAssembly binary is called a module. Modules are typically embedded in a host environment. For instance, the browser's scripting engine or WASM time are embedders, we will also call them hosts or runtimes. WASM modules can export typed functions so that the host can call into the WASM module. Similarly, a WASM module can import a function from the host environment. This is like the extern keyword in C. The host should provide the requested functions when instantiating the module, which is similar to the, linking a shared object. Let's go over an example. We don't want to write WebAssembly directly, so we will write a very simple C code, then transpile it into WebAssembly. Here we have a logInt function that takes an integer parameter. This function is imported in this example, so we don't define it here. Then we define an add function that takes 2 integers and adds them up. We will compile this code using the mscripting compiler, which will give us the binary format test WASM as the output. We don't have a main function. We will use the side module setting here. mscripting emits a few extra symbols because of this, but it's not important right now. On the right side, you can see the hex dump of the output. Since the binary format is not human readable, WASM files can also be represented in text format. We can use WASM to VAT tool in WebAssembly Binary Toolkit to convert the binary into the text format. There are some unused symbols in that mscripted emitted here, so I grayed them out. If we get rid of them, we'll have a cleaner code here. It's the same code. Add is an exported function in our C code, so add is exported. And logInt is imported from the env namespace, so you can see the env keyword there. In WebAssembly, all import names have a namespace. When we run WebAssembly, we must provide all imports or else the module won't run. And we can write the text format by hand and then use the VAT to WASM tool to convert it to binary WASM format below. Let's try this let's try running this in JS. We define an imports dictionary here and add the env log int function here. This way we expose the function to the WebAssembly module. Then we find the exported add function and call it. The output should show 3 twice because we both logged and returned the results in our code previously. So note that the module can write to the browser's console only through the logint function that we define here, and it has the console log here because we deliberately exposed it here. So the module is sandboxed otherwise. Earlier, we said that WebAssembly only has integer types. So if we want to pass strings, we have to get a bit creative. First of all, we should define a memory, the one-to-one, that one at the end that we tell that we want 1 page initially, and our maximum memory is 1 page as well. Just for to give an example here, we also export it here so that the host can access it. We use data directive to write 2 string literals at offset 1. Then in the say hi and say bye functions, we pass their pointers to the imported logstr function. The host side is a little more complicated. The module only gives us the offset of the string. We should actually read it from the memory. We exported the memory from the WASM side, so we should be able to get it as an export here. So let's try that. And MDN WebDocs tells us that the WASM memory object has a buffer property that we can use as an uint8 array. So let's do that. Uint array also has a slice method. We can use it to get the offset. Slice normally has 2 parameters, the start and end of the range, but we don't know the end because our strings are null terminated. And finally, we can use text decoder to convert bytes into a string. This looks okay, but it doesn't work. The reason is that JavaScript does not have null terminated strings. Its strings have a pointer and a length. Because we didn't give the slice an end earlier, we're trying to print the rest of the memory here, which gives the wrong output for the first call. We can fix this with a second slice from the null byte. This works, but this is language-dependent behavior. Earlier, we had said WASM was polyglot, but most hosts must expect null-terminated strings here. Another problem is with allocations. Let's see an example. Let's say our module performs string concatenation. This requires allocations, so I wrote a very simple bump allocator here to keep the example minimal. We compile this with mscripten. The concat function takes 2 pointers and returns the result pointer. We also need to allocate the function input parameters. That's why we also exported the alloc function. When we use the module in JavaScript, we have to call alloc first, get offset, write bytes to the WebAssembly memory. Then invoke concat with both input offsets. When concat returns the result offset, we must read its bytes from the WASM memory. Once again, we have to assume that these strings are null terminated. This time we also needed an alloc function from the WASM module. But if someone else was writing the module, then nothing guarantees that the module has an alloc function. So the host and the guest should agree on a contract. Rust has a solution to this problem. It's called WASM bindgen. You annotate your import and export functions with the WASM bindgen macro, and Rust generates some glue code for the JavaScript side as well. This compiled module is a bit different. There's an export name, you can see it here, just like our alloc function. Also, we import a function, but its name is garbled, like you can see it here. Let's see the glue code next. So here's the glue code. The import with the weird name can be seen here. It's just a wrapper around the logstr function. it handles the string passing logic. Similarly, WASM bindgen wraps the say function for us so that the strings are allocated and passed to the WebAssembly side. Then we can use the functions without knowing how memory is managed. This is neat if you're running Rust in the browser, but it doesn't extend to all languages, so we need a universal standard for this. And that's what WASI is. WebAssembly System Interface is an initiative to provide a modular system interface for WebAssembly. It consists of an API imitating the libc system calls. So it exposes things like standard output or environment variables. WASI also defines an application binary interface, an ABI, so that, for instance, all languages can pass the strings the same way. Here's an example in Rust. On the top, we compile this program as a normal binary, and on the bottom, we compile it to the WASI target and run it with the WASM time engine. The result is the same. We can also use the WASM time engine as a library. Let's create a simple module first. Here in main, we call a factorial function in a loop. We import the factorial function from the host side like this. Then we compile it to the WASM32 WASI target. This will allow us to use things like println here. And you can see the outputs. For the host side, we create another Rust project. Then we add WASM time as a dependency. In the main function, we create an engine, a linker, and a store. Engine runs the code and linker manages the functions. Store holds the execution state. We have none, so ours is empty. Then we pass the factorial function to the module, read the module from the WASM file, and then find and call the main function. This does not work. That's because we didn't enable WASI functionality on the host side. So let's do that. We first add the WASI common dependency, as in here. Then we pass WASI functions to the linker. This enables functions like println for the module. WASI also has some state-like enabled capabilities. It's called WASI context. We create one and pass it to the store. We also explicitly enable standard input here. Unless we do this, the program cannot print anything. This is great for security because it allows us to control each API separately. So for instance, WASI can allow you to read file from the file system, but since we didn't enable it here, it doesn't work. And that's it. If we run the program now, we'll see a nice list of factorials. We are running WebAssembly outside the browser. WASI is great because it works across different languages. For example, here is a runtime in C running our Rust module. We are using WASM micro runtime as a runtime library. The output is the same. And WASI gives us POSIX-like features like file I/O sockets on top of WebAssembly's portability. And Solomon Hykes, Docker's founder, tweeted that Docker wouldn't be needed today if WASI existed in 2008. In fact, Docker can host WebAssembly modules today. You can use different runtimes and get the same results. WASM modules are typically smaller than containers, and they're not specific to the CPU architecture. WASI is still being actively developed. The first major iteration of WASI standard is known as Preview 1, and it provided the POSIX-like API we saw before. WASI Preview 2 was launched in January this year, and it greatly extends the capabilities of the WASM ecosystem. Preview 1 improved the interoperability between a WASM module and the host, and Preview 2 aims to extend this to interactions between WASM modules. Also, WASI Preview 1 provided us one fixed POSIX-like interface that a command line program would need. For library-like behavior, we want to define many custom composable interfaces designed for specific tasks. Preview 2 defines a component model for these interactions. In the simplest terms, a WASM component is a module wrapped in an interface. The interface describes the imports and exports of the module in a higher level way using the with format, WASM interface type. These can then automatically be compiled to comply with the canonical ABI standards. The component model also defines how the memory is used. For example, components never export memory, they always import it. With files contain interfaces or worlds. They provide a higher level model of the components. A with file does not define behavior, it only specifies contracts between these components. Two main concepts here are interfaces and worlds. A with file contains one or more interfaces or worlds, and an interface is simply a bundle of types and functions. This is very useful for defining logically relevant definitions together and giving them a name. You can refer to interfaces from other places, import or export them. An interface also can import another interface. Here's an example canvas interface that defines a drawline function and the types that the function uses. The canvas ID type is simply a type def for U64. Point is a pair of U32. Values defined as a record. This is just like a C struct. With has many built-in types like strings, enums, optional values, tuples, variants, and more. The specification in the link I have here describes them in detail. A world, however, defines a bundle of imports and exports. A component is described by the world it conforms to. So this defines the functionality that the component depends on and what it provides. You can import and export functions directly here and use interfaces like this. So let's see how with files are used. Let's build the components from scratch first. To keep things simple, at first we will write this one by hand. So let's write a module which exports an add function. On the right side is a corresponding with file. I want to use this adder functionality later, so we put it in an interface. We also define a world that describes the module and export the adder interface. That means we will be exporting an add function. Note that there's some namespacing involved with the export's naming so that it matches with the with definition. It tells us that we're implementing the add function under the adder interface in the example component package. On the left side, we simply convert the WAT file to WASM like we used to. If we dump the sections in the WASM file, we get 4 sections. And on the right side, we use WASM tools with the embed command to inject the with file in the WASM module. If we do that and dump the section headers, we see that there are 2 new sections named name and component type. You can embed custom data sections in WASM files like this, and we use it to store the with file in the module here. These will be used when we componentize in the next step. We use WASM tools again with the new command. This command uses the injected with sections to turn the module into a component. The binary representation of a component is slightly different than a module's, so using the old WASM object dump tool on this component file will return an error. This is no longer a WASM module, so we use the WASM tools print command to dump its contents instead. Right from the start, the file does not start as a module. It says component. We can see that the original module definition is there, almost untouched. There is an added producers field, but that is simply some debug info. Outside the module definition, the component goes through steps to basically re-export the add function. There's a canon lift statement here. What it does is it takes the inner module's add function and wraps it in a way that conforms the canonical ABI. if our function had more complex types in it, this wrapper would take care the necessary conversations. For add, it will simply pass the parameter it receives. Here's how we load and use a component with WASM time. First of all, we create a Rust project for the host and add WASM time as a dependency. We did the same for running a module, so I won't show you the cargo file. It's the same. We do a few things differently to load a component instead of a module. First of all, there's a bindgen macro here. This tells Rust to load the example world from the add with file. This will generate a type named example and that example that has an add function in it so that we can use the component like a regular Rust type. In the main function, we don't use engine default this time. Instead, we should tell WASM time that we will be working with the component model, so we pass a custom config and set WASM component model to true. We create a store and a linker just like before, but then instead of calling module from file, we call component from file. Instead of going through the linker to get an instance, we call the generated example instantiate function. This will give us the example components. Using the component, we can reach into the interface scope by example component adder function here and call the add function by the generated function that we have here, the call add function. This is a typed function, so we can't accidentally pass, for instance, a string here. That's it. We just use the component. Instead of writing the conversion functions ourselves, the component bindgen macro prepared them for us, and the result is 46. Let's write a second component that depends on our adder. This one is called twice. It simply adds the number to itself. To do that, we use an imported add function. With WASI preview 1, this add function would have to be on the host side. With preview 2, we can use another module as a dependency. First, we import the example component adder add function like this and export a twice function. The with file is like this. I copy pasted the adder instance so that we can read it, but normally you place it in a common with file and import that. The example2 world imports the adder interface and exports the twice function. We can build and componentize this module using the embed and new commands. Then we use the compose commands on twice component and show add component WASM as a dependency. This gives us the composed component. Alternatively, we can use the WASM Builder app website to visually compose these two components like this. So this is the compose example, or we can use the WASM Builder app. Either way, we get a composed component that only exports the twice function. The add function is satisfied by the dependency add component. This is a lot like using a static library because the code of the add component is embedded in the composed components. But notice that the two components don't even have to be in the same programming language or use the same memory model. We can still compose them. Okay. Sorry, did I miss something? Okay. WASI Preview 1 used to hardcode its application binary interface. Instead, Preview 2 describes its ABI in separate interfaces. While these standardized interfaces support OS features, these interfaces could be compatible with native applications. However, in different use cases, such as cloud, this might not be the case. Different work groups have been proposing other instances and interfaces for instance, Basic Cloud Core here. Instead of a file system, cloud applications need access to blob stores, databases, and key value stores like Redis. Um, WASI Cloud Core attempts to standardize these interfaces. These are interfaces to conform while writing the components, but for sharing the components themselves, we need a registry like Docker Hub. Bytecode Alliance is working on a registry protocol for WASM components called WARC. When it's ready, we will be able to share common functionality over its as components. There's also WASMer, which is another registry that currently has more than 100, I guess, WebAssembly applications. These are not components, though. They are WASI applications treated as executables. Um, WASI Preview 3 will have native support for async operations, features, and async streaming. With this, WASM components will be able to handle streaming data without blocking, such as an open TCP connection. There are also proposals for things like a threading system and a garbage collector. These are all works in progress, but we will see where it takes us. In the remaining slides, I will go over some interesting applications of WASM outside web. One of the more obvious use cases of WASM is in serverless platforms. In 2017, Cloudflare made its edge network programmable using Chrome browser's JavaScript engine V8. It was quite novel back then because other services were spinning up dedicated micro VMs, containers, or processes per each function. Cloudflare used the isolates functionality in V8, which is a single-threaded sandboxed execution context for JavaScript. This meant that they could run multiple functions safely in the same process. A year later, they also introduced WASM support through V8. Workers is not a WASM first platform, so their WASM execution has some overhead and latency. Their documentation still recommends writing the workers in JavaScript instead, but I just wanted to mention this for its precedence. Versal also added WASM support through JavaScript in the same way. Fastly has WASM support on their compute platform, but they run a WASM engine instead. Shopify recently added a feature called Functions, which allows users to extend the platform's capabilities. For example, you can define a discount during checkout for some items that go together. Obviously, the host side is not open source here, but there's a Rust crate for the guest side, and we can examine it. It has some macros to reduce boilerplate. You write your function to have one input and one output like this, and you annotate the function with the Shopify function macro here. The macro generates the main function for you, which reads the standard in for a serialized JSON input and deserializes it to the given type, calls your function, and then serializes the output to standard out. The host does not expose any other functions to the module, so it has a simple request response flow. However, the module is paired with a GraphQL query file, which is executed just before the module. The output of the query is passed as the module's input, so they combine the power of declarative and imperative programming this way. This standard in, standard out trick is standard input output trick is used widely in scenarios where the business logic is in the WASM module is exposed as a one function and it never calls host functionality. Another example would be the WASM plugins in SQLC or SQLC tool, which does the same thing except it uses protobuf for serialization. Some serverless platforms like Fermion Spin and Hippo use WASM for handling HTTP requests. To do that, they repurpose a 30-year-old protocol called CGI. CGI was mostly used in servers to run C code in the backend. So essentially, this is how it works. The server receives a request, finds the handler program for the requested route, and starts the program in a child process. The server adds an HTTP prefix to the request headers and passes them to the child process as environment variables. If there is a request body, it is sent through the standard input. Then the child program's standard output is read and returned as a response. As long as the child processes conform to these rules, handlers could be written in any language. So people in DS Labs replaced the handler process with WASM module and called it WebAssembly Gateway Interface. Writing handlers this way is very simple because the entire protocol is text-based. However, this is hard to adapt to the other protocols. Also, the handler module cannot make calls from the host using this model alone. By the way, if you want to run WASM code on the Apache server, you can use mod WASM extension module. I also provided links for these resources. So we mentioned fermion spin when discussing WAGI, but WAGI is not the only protocol they implement. In fact, Spin releases SDK libraries for languages like Rust, Go, Python, .NET, or NIM that contain wrappers for low-level functions. If you use the SDK, your binary does not need to target WASI. They define low-level records for each endpoint and custom serialize each field. The serialization code is auto-generated in advance. Here we see the HTTP handle request callback in the module. The host calls this function by serializing and passing each field for an HTTP request. The SDK code collects these fields into a spin HTTP request t-type struct. Then the typed function is called. This one calls the user code. The result is written to the response struct, which is then serialized into a just 28 byte slab called red area. Now I found this very interesting. In order to avoid another allocation during the return, they write the response to a static memory range. This works because the handler function is blocking and it's never called in parallel. So basically all HTTP responses return the same pointer. Those 28 bytes are written over and over again. Fermion is working on a Spin 2.0, which is based on the component model that comes with WASI Preview 2. They're already using WIT files to auto-generate these headers, but in the future, these will be used for defining all of their interfaces. And another example, WASM Cloud lets you run distributed WebAssembly actors on the cloud. The communication between the host and the guest is bidirectional, so WAGI cannot work here. So they implement the WASM bus protocol instead. Modules do not need to support WASI, but the WASM bus library must be imported to the module, which is implemented for Rust, Go, Python, and JavaScript only. WASM bus is recently deprecated, and WASM Cloud is moving towards WASI Preview 2. Xtism is a plugin system, much like WASM bus. It invents its own communication protocol too. Xtism calls its imported library a plugin development kit. The host side is called the software development kit. Xtism supports many languages on the host side as well. As you can see, people came up with many solutions to this problem of standard WASM calls. That's because WASM Preview 2 took 4 years to release. Another such protocol is WebAssembly Procedure Calls, or WAPC for short. There's also WASM RS, which implements asynchronous reactive streams for WebAssembly. The Candle platform uses these, as far as I know. We saw WebAssembly being used on the cloud, and for serverless applications, cold start latency can be very important. The faster your module starts to work, the better. So WebAssembly modules have such a simple memory model. You can snapshot a program by just storing its memory array. And that's what Wiser does. If you have some state that you want to pre-initialize, you can bake them in your module using Wiser. The init function is called during compile time, and the memory state at the end of it is embedded to the module. So the next time you load it, init is already called and you save some time. And another project playing with the memory snapshot idea is Flawless Dev. With Flawless, each host call also persists the WASM memory. This way, if the program crashes, no state is ever lost. So it's an interesting idea, but still in development, and no source code was released yet. Another use case of WASM is emulating JavaScript engines on non-web environments. People at Bytecode Alliance added a WASI target to Mozilla's SpiderMonkey engine so that it can be compiled into a WASM module. They use Wiser for storing the initialized state of the engine. Also, even though just-in-time compilation doesn't work, they store some inline cache stubs to run some common code patterns in near native speed. You load the WASM module on WASM time, pass the JavaScript file contents, and it runs the file on this WASM virtual machine. If the script is malicious, it has no way of accessing the system resources. This is great for running untrusted JavaScript code without too much sandboxing effort. The same technique can be used for running other languages like Python or Lua on WASM. I really recommend the article on the topic. It's an interesting read. WebAssembly modules can easily be converted to a subset of C using the WASM to C tool. This has some interesting results. First of all, RLBox and WASMBox-C are similar tools. You compile an untrusted legacy code, source code to WebAssembly, and then convert the module to C, then compile that. Since you end up with native code, you don't need a WASM runtime, but the code is still sandboxed. Firefox uses this for isolating some external C libraries. WASM2C is also used for bootstrapping the Zig compiler. Compiler bootstrapping is a very complicated problem, and different programming languages approach the problem differently. For instance, to build the OCaml compiler, you first compile the old compiler to an imaginary bytecode target. Then this version is interpreted using a tiny emulator so that it can compile the new compiler in a portable way. Zig does a similar thing, but instead of making up an instruction set, they use WebAssembly. And instead of emulating, they use WASM2C, so the first compiler is also very fast. One of the strongest aspects of Rust is its macro system. Rust has two types of macros, declarative and procedural. Declarative macros are easy to write. They are similar to C macros, but they generate tokens instead of raw strings. So the code hygiene is much better. Procedural macros are harder to write, but they basically let you run code in compile time to transform the token stream. So there are very powerful use cases of this. One example is SQLX. SQLX takes your SQL queries and connects to the database at compile time to verify that the query matches the database schema. It is beautiful, but obviously a macro being able to make arbitrary network requests is, it's a little scary and dangerous. So David Tolnay came up with WAT. It is a small WASM runtime for running procedural macros in an isolated context. You basically modify the macro slightly to export the symbol, compile it to the WASM unknown target. So WASI is not needed. Then add a second crate to load and run the resulting WASM file. The inner logic of the macro will be run in the WASM runtime, so it cannot access any external resources. And another advantage is that the macros are pre-compiled, so they don't increase code compilation times. It's not widely used, but I think it's an interesting use case for WASM. And HarfBuzz. HarfBuzz is a widely used text shaping engine for mainly OpenType fonts with version 8.0 that was released on July 2023. It now supports a WebAssembly shaper. Normally, HarfBuzz uses an OpenType shaping engine, which is given a buffer of code points for a text and turns them into glyphs and positions them. With the 8.0 update, you can now embed WASM code in your fonts, which then HarfBuzz uses to shape the text instead of using its OpenType shaping engine. There are many practical use cases for this. The examples repo lists a WASM shaper for a Nastaliq Urdu font. Apparently, kerning for the Nastaliq writing system in Urdu is very contextual, and handling it in OpenType requires implementing many edge cases by hand. So with WASM, we can just program these cases in about 600 lines of code, resulting in 100 kilobytes smaller fonts with correct kerning. Another example is shadow painting for fonts. OpenType paints glyphs one by one, so shadow fonts like this often do not work. And another example is shadow painting for, instead we can write a WASM shaper that first paints the shadows, then goes all the way back and does a second pass of the foreground characters. A trusted execution environment, TEE, is a hardware isolated area of a CPU that allows applications to perform secure calculations. There are two types of TEEs, process-based and VM-based, and the development models between the two differ significantly. As a result, application developers must rewrite the code for each specific hardware platform. Inarcs is an open source framework for abstracting away these details. They provide a WASM time-based runtime that runs on the TEE instance, which they call Keep. The runtime supports WASI, so developers can write code in their preferred programming language. So I think that's about it. Thank you all for listening. And if you have any questions, I'll gladly answer them.
Thank you so much. So now I'm checking the Q&A function on the bottom of the screen. So everyone, you have a chance to raise some question to Bengisu. Actually, we have one question, but I think it's more to me than to you, Bengisu. It's about, do you apply other programming languages and technologies in your business in Turkey? So I will take it, this one. Yes, we have multiple projects in Luxoft Turkey where we apply different technologies, different programming languages, different than what you saw today from Bengisu. It was just one of the examples of what we apply during our daily work. So if you are interested to learn more, we have a lot of public resources that you could reach our team, and we will come back to you with specific answer to your concrete questions. So let me see if we have a few more questions. What is the work model in Luxoft? In office, remote, or hybrid? So we are applying all of these models. It depends on the role, depends on the project and the industry of the project that we are dealing with. As I mentioned during at the beginning of this event, we have two offices already established in Istanbul. but outside Istanbul, we have also several colleagues, several employees who are working from different parts in Turkey, like Ankara, Izmir, etc. So if you are interested for a concrete city and format of work, please reach us and we'll discuss according to the specific job role and the conditions of the project that we have. We have one more question. How do you see the future of WebAssembly evolving and its impact on web development? So, Bengi, so this is for you.
I really think that it has a huge potential, not just in, by the way, not for JavaScript, but every sector. I really wanted to mention this during my presentation, but it has even a potential in, you know, automotive and any industry you can think of, because you can have a different virtualized environment. So um, for JavaScript, to be honest, I let's say the best part of WebAssembly is you can really use whatever language you want. So and honestly, some of the features of JavaScript makes it harder to, you know, have performant codes, especially since it's, you know, it's a single threaded language and so on. Um, so I think the introduction of WebAssembly into the web sphere will come with its perks, and that would definitely be performance, and in some native applications as well. I mean, imagine Electron.js if it was written in something else. To be honest, it would be a lot faster, and we're using it daily, so we would have like a faster VS Code. So yeah, I hope I could answer your question.
Thank you. We still don't have reaction from the person who raised that. So I believe you managed to answer. Newbie.NET Dev using C#, ASP.NET Core, etc. is WASM a necessary tool to learn for Turkey's software marketplace?
I can answer the question. It's not necessary, but I think it will play a pivotal role in the future. I mean, WASM will play a pivotal role in the future. So learning or getting familiar with it would be nice, really nice to have for personal development. So, but it's not necessary for uh, not in Turkey, and I don't think it's necessary in other parts of the world too, for especially .NET environment.
Yeah, I think as well, actually, it's more or less overlaps with what I shared earlier to one of the previous questions, that we have a very big portfolio of different projects and technologies that we apply in our business. That's why nothing is mandatory or is the only one tool and technology that you could use. There are multiple opportunities. Okay, so we have another question from Hikmet. Let's suppose that we have a system that squeezes JPEG files to 1/4 part of the original size. Does this replace the federated learning? Bengi, so I think it's this is in your area.
I'm not sure if it's related to WASM, but I mean, federated learning is a different concept, and I'm, to be honest, I'm not sure. I mean, it's not a domain I really have experience in. So, but if you ask that if WASM has an approach for this, and will that replace the federated learning? I mean, it It can be, but that I mean, it really needs to be studied so that I can, give an answer to this.
Thank you. Thank you so much. So we are at the end of our session. I would like to share with you all of the ways and channels that you could reach our team, ourselves, via social media. So we have a global account via Facebook. If you don't like to use this social media, you can find us in LinkedIn. Just type right in the search field Luxoft Turkey. So we have a live page there. So you can find it in Instagram with a lot of content and updates from our company. Perhaps most of you know that we are presented in more than 50 countries around the world. So definitely you can find a lot of interesting news from technology, from IT industry, and etc. You could find us in Twitter, and you could follow our YouTube channel, where, as I said before, we'll upload the recording of this webinar for your further references or just checks later on. I would like to thank to all of you for visiting our first webinar that we're doing in Turkey. We'll try to make this kind of events more often with interesting speakers like Bengisu. Special thanks to Bengisu for her topic today. It was interesting, and I believe that we can give more knowledge and more updates to our audience in the country.
Thank you all for joining and being here. And you can also contact me for anything about the slides, the resources I used, and WASM too. So yeah, thank you all for joining.
Thank you all. Have a nice evening, and
have a nice evening.
Stay in touch with us. Bye-bye.
Bye.